Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today we are going to discuss about a module entitled Generalized Uncertainty Principle under the paper Quantum Mechanics 1. So students, let us see what all we are going to learn in this module. Firstly, we'll get to know the definition of the root mean square deviation and its significance. We'll learn how to deduce the generalized Heisenberg's uncertainty relationship for any pair of canonically conjugate variables corresponding to non-commuting operators. We'll then get to learn how this general relation is used in the case of 1. Position and its conjugate momentum variable, 2. Between the components of the orbital angular momentum. We'll then know the state in the coordinate representation which corresponds to the minimum uncertainty product delta x delta px is equal to h cross by 2 pi, or the uncertainty in determining the position and the uncertainty in determining the momentum is equal to h cross by 2 in the position and momentum variables of the particle. We'll get to learn the meaning of invariance of trace of the operator, and then we will know why the uncertainty relation in energy and time cannot be considered analogous to that of the canonically conjugate position and momentum variables. Up till now, we have studied in qualitative terms the statement on Heisenberg's uncertainty principle in terms of the uncertainties in position, that is delta x, and the uncertainties in momentum, that is delta p. Now, the component of angular momentum and its canonically conjugate variable also is something that we have studied. So here we shall study how this principle is derived formally in general terms by introducing the uncertainties delta A and delta B associated with the measurement of the dynamical variables A and B in a given state. We shall use the generalized uncertainty relation to find out the uncertainty relation between the components of orbital angular momentum. We shall also derive the expression for the wave packet which represents the minimum uncertainty in position and momentum variables. Root mean square deviation. Now, the definition of the root mean square deviation can be taken as the measure of the spread in the values that are being measured. So, for example, the spread delta A associated with the measurement of some quantity A in a given quantum mechanical state psi can be defined as delta A whole square is equal to the expectation value of the square of expectation value of operator A, and this turns out to be equal to the expectation value of the square of operator A minus twice the expectation value of the operator A times the expectation value of the operator A plus the expectation plus the square of the expectation value of the operator A, and this gives the final value of delta A whole square, that is the spread associated with the measurement of A, as expectation value of the square of the operator A minus the square of the expectation value of the operator A. Similarly, if we consider any other Hermitian operator B, which is there defined in a given quantum mechanical state, then for that also we can write down the result of the spread of the values of B given by delta B square is equal to expectation value of the square of the operator B minus expectation value of operator B. And this, as obtained earlier for the case of the measurement of A, here we get the spread of B, that is delta B square, given by the expectation value of the square of the operator B minus the square of the expectation value of the operator B. And using these two results, one can then write the general statement for the spread of the values associated with a given measurement and define the quantity operator E is equal to operator A minus the expectation value of operator A, and operator F is equal to B, operator B minus the expectation value of operator B. And let us consider the state phi given by state phi is equal to bracket open operator E plus iota times lambda times operator F bracket close acting on the state psi. Derivation of the statement of the root mean square deviation. So as we have defined earlier that the state phi defined as bracket open operator E plus iota times lambda times operator F bracket close times state psi, where for simplicity let us assume that lambda is real. Now since the operator A and operator B are Hermitian operators and so are the operators E and operators F, therefore we can write that the scalar product of the state psi with itself, that is bra vector state psi ket vector state psi, is equal to bra vector state psi then bracket open operator E minus iota times lambda times operator F bracket close whole times bracket open operator E plus iota times lambda times operator F bracket close acting on the state psi. So basically the scalar product of the state phi with itself is given by this relation, and this is greater than or equal to 0, or in other words we can also say that the bra vector state psi operator E square plus lambda square operator F square plus iota times lambda times the commutation relation of operator E with operator F, all these operators acting on the state psi, is greater than or equal to 0, where we note that the commutator of operator E and operator F is given by the commutator of bracket open operator A minus expectation value of operator A bracket close and bracket open operator B minus expectation value of operator B bracket close. And this is, if we expand this term and solve it, then we get that this is equal to the commutator of operator A and operator B. So we can say that the commutator of operator E and operator F turns out to be equal to the commutator of operator A and operator B. Rewriting the above inequality in terms of the result that we have just derived, we can say that the bra vector state psi bracket open operator A minus the expectation value of operator A bracket close whole square acting on state psi plus lambda square times bra vector state psi bracket open operator B minus expectation value of operator B whole bracket close whole square acting on state psi ket vector state psi plus iota lambda times bra vector state psi commutator of operator A and operator B acting on the ket vector state psi, and this is greater than or equal to 0. So basically we've just plugged in the values that we have obtained over here in the above inequality, and then the left hand side has its minimum value when its derivative with respect to lambda is 0, and when we do this the result that we get is twice lambda times delta B square plus iota times bra vector state psi commutator of operator A and operator B acting on ket vector state psi is equal to 0, or lambda is equal to minus iota times the expectation value of commutator of operator A and operator B in state psi upon twice delta B whole square. Uncertainty relation. Now, substituting this value of lambda in the above inequality, we get, after simplifying the inequality, the relation delta A whole square times delta B whole square is greater than or equal to 1 minus of 1 by 4 times the square of the modulus of the expectation value of the commutator of the operators A and B with respect to the state psi. Or if we solve it further, we get that delta A square times delta B square is greater than or equal to 1 by 4 times square of the modulus of 1 by iota times the expectation value of the commutator of operator A and operator B in the state psi, that is bra vector state psi commutator of operator A and operator B acting on the ket vector state psi, and this is greater than or equal to 1 by 4 times square of the modulus of the expectation value of operator C, that is bra vector state psi operator C acting on ket vector state psi, where we have introduced the relation that the commutator of operators A and B is given by iota times operator C, and where the operator C is a Hermitian operator. And from the above inequality, we obtain the result that delta A times delta B is greater than or equal to 1 by 2 times the expectation value of operator C. And this gives the general statement of the uncertainty principle for any pair of commuting Hermitian operators, operator A and B, will satisfy the commutator relation. Commutator of operator A and operator B is equal to iota times operator C. In particular, for the commutator of operator A and operator B to be equal to iota times H cross, we have delta A times delta B is greater than or equal to half H cross. And for the commutator for operator X, operator Px is equal to iota times H cross. Therefore, using the above general result, we can write down the result for delta X times delta Px as delta X times delta Px is greater than or equal to H cross by 2. And this is the precise statement of the uncertainty principle. Uncertainty principle for the angular momentum. Now, the generalization to 3 dimensions is rather straightforward. The uncertainty relation between the components of momentum operators. The commutation relations for the components of the angular momentum operators can be easily worked out. That is, we can see that the commutation relation for the x and the y component of the momentum operators, the angular momentum operators, turns out to be commutator of the angular momentum operator in the x direction and the angular momentum operator in the y direction is equal to IH cross times, within brackets, the position operator along the x-axis times the momentum operator along the y-axis minus the position operator along the y-axis times the momentum operator along the x-axis, and this turns out to be equal to IH cross the angular momentum operator along the z-axis. So in that sense, the commutator relation between the components of the angular momentum operator along the x-axis and the y-axis are given in terms of the angular momentum operator along the z-axis. Similarly, we can show the commutator for the y component of the angular momentum operator and the z component of the angular momentum operator turn out to be equal to IH cross the x component of the angular momentum operator. And similarly, the commutator for the z component of the angular momentum operator and the x component of the angular momentum operator turn out to be equal to IH cross y component of the angular momentum operator, where h cross is equal to h by 2 pi and h is the Planck's constant. Now, applying the generalized uncertainty relation for the components of angular momentum operators, we get delta Lx delta Ly, that is the uncertainty in the angular momentum component along the x-axis times the uncertainty in the angular momentum component along the y-axis is greater than or equal to h cross by 2 times the modulus of the average value or the expectation value of the z component of the angular momentum operator. That is, the uncertainty in the product of the measurements of the x and the y components of orbital angular momentum is determined by the expectation value of its z component. Examples using uncertainty relation. Now let us consider a simple example of a linear harmonic oscillator to estimate the minimum value of the 0-point energy using the uncertainty relation. So, to take a simple case of a one-dimensional harmonic oscillator, and then let us write the expectation value of the position operator, that is operator x, and this turns out to be 0. Also, the expectation value of the x component of the linear momentum operator, that is expectation value of the operator px, also turns out to be 0. Therefore, the spreads delta x is equal to under the root of the expectation value of the square of the operator x, and delta p is equal to under the root expectation value of the square of the operator p. Turns out to be that since both the expectation value of x and expectation value of px is 0, therefore in the case of simple harmonic oscillator in one dimension, both x square and p square are positive, and thus we have that delta x is greater than 0 and delta p is also greater than 0, so that the product of delta x and delta p is greater than 0. In fact, we can see that the product of delta x and delta p is greater than or equal to h cross by 2. Here it is important to see one point, that while the expectation value of the operator x comes out to be 0 and that of the operator px also comes out to be 0, but when we are calculating the expectation value of the square of the operator x and the expectation value of the square of the operator p, then those values do not come out to be 0. And the reason for that is what we had discussed earlier in the case of root mean square deviations, that while for quantities like harmonic oscillators where the mean of a quantity like the displacement comes out to be 0, but the mean of the square of the displacement is not 0, and therefore the root mean square value of the displacement will not be 0, and thus we can actually find out the spread in both the position as well as the momentum. And this important consequence is that the lowest energy, called the 0-point energy of the oscillator, is different from 0, estimating 0-point energy of oscillator. Now, once we have understood that when we take the root mean square deviation, then the final values are not 0 but are greater than or equal to h cross by 2 in the case of delta x times delta px. So one can now find out the lowest energy, called the 0-point energy of the oscillator, and this turns out to be different from 0. So in order to make the estimate of this energy, let us proceed as follows. Let us first consider the energy eigenvalue given by the expectation value of the Hamiltonian operator in the state psi, and this is equal to 1 upon 2m times the expectation value of the square of the momentum operator plus half k times the expectation value of the square of the position operator, where k gives the potential energy term, or k in this case represents the force constant. Clearly, the minimum value of the energy is given by 1 by 2 times m whole times delta p square plus k by 2 times delta x square, and this is greater than or equal to 1 by 2 times delta p square plus h cross square k by 8 times 1 upon delta p square. In other words, the minimum value of the energy or the 0 point energy of the oscillator is given by 1 by 2 times delta p square plus h cross square k by 8 times 1 by delta p square, where the E minimum is equal to E0 is the 0 point energy of the oscillator, and this can further be written as delta p square by 2m plus h cross square k by 8 times delta p square minimum, where the value of the expectation value of the square of the operator x has been written in terms of the delta p square. Further, delta p naught square is equal to 1 by 2 times h cross square times k times m to the power half, and this is equal to m by 2 times h cross omega c, where omega c is the classical frequency of the harmonic oscillator and is given by omega c is equal to under the root of k by m, where k is the force constant and m is the mass, and we get the 0 point energy using that substitution as E naught is equal to half h cross times omega c, states with minimum uncertainty product. The equality sign appearing in the uncertainty relation depends on the nature of the state vector of the system. From the relation bracket open operator E plus iota times lambda times operator F bracket close acting on the state vector psi is equal to 0, it is clear that the equality sign occurs in those states for which the value of lambda is given by lambda is equal to minus iota times expectation value of the commutator of operator A and operator B in state psi upon twice delta B square, and this is equal to the expectation value of the operator C in the state psi upon twice delta B square, where the commutator of the operator A and operator B is equal to iota times operator C, and for the more specific case considering the position and the momentum operators, the commutator of the position operator x and the momentum operator p turns out to be equal to iota times h cross times operator I, that is the identity operator or the unit operator. For the operators E and operator F, let us choose the operator E as given by operator A minus expectation value of operator A, and this is equal to operator X minus expectation value of operator X. Similarly, the operator F can be written as operator B minus expectation value of operator B, and this further for our case becomes operator P minus expectation value of operator P. Substituting the relations in the first equation, we can then get the following equations. Wave packet for minimum uncertainty. Now, the relations that we have obtained for operator E and operator F, when we substitute these relations in the equation obtained earlier, then we can rewrite the equation for uncertainty as bracket open operator x minus expectation value of operator x bracket close acting on the state psi plus iota times h cross by twice delta p square whole times bracket open minus iota times h cross times derivative with respect to x minus expectation value of operator P, bracket close, whole acting on the state psi, and this should be equal to 0. So multiplying this equation from the left by the bra vectors state x and identifying that bra vector state x ket vector state psi is equivalent to the wave function psi as a function of position x, we get bracket open operator x minus expectation value of operator x acting bracket close acting on state psi plus iota times h cross by twice delta p square whole times acting on bracket open minus iota times h cross times derivative with respect to x minus expectation value of operator p bracket close acting on state psi is equal to 0. This is the first order differential equation in the wave function psi, which can be solved to give the value of the wave function psi as a function of position x is equal to n times exponential to the power bracket open minus delta p square by h cross square whole times bracket open x minus expectation value of operator x bracket close square plus iota times expectation value of operator p times x upon h cross whole bracket close, where n is the normalized constant to be evaluated from the condition integral square of the modulus of the wave function psi as a function of position x evaluated over dx is equal to 1. So basically this means that the probability of finding the particle in the space has to be 1, and which gives the normalization constant as 1 by 4, and which gives the value of the normalization constant as bracket open twice delta p square by pi h cross square bracket close whole to the power 1 by 4. So we have thus obtained normalized wave function for which the minimum value is given as delta x delta px is equal to h cross by 2. Time, energy, uncertainty. Now we shall study the uncertainty relation between time and energy. We must first note that the wave function has the form of a Gaussian function modulated by the oscillatory factor exponential to the power iota times the expectation value or of the operator p times x upon h cross. This factor, being of unit modulus, does not affect the probability density square of the modulus of the wave function psi, which is Gaussian, having maxima at x equal to the expectation value of the position operator x. So the square of the modulus of the wave function psi, that is the probability density, turns out to be equal to 2 pi times delta x square whole to the power half, where delta x is the uncertainty in position, this whole times exponential to the power minus within brackets x minus the expectation value of the position operator, this whole square, upon twice the square of the uncertainty in the position, that is twice of the square of delta x. Thus this Gaussian function or the Gaussian wave function describes the wave packets with minimum uncertainty. Now let us come on to the time energy uncertainty. So we must note that while there does exist time energy uncertainty relationship of the form delta E times delta T is greater than or equal to h cross, where delta E is the uncertainty in the determination of energy and delta T is the uncertainty in the determination of the instant of time when this energy is being measured, it should not, however, be regarded as analogous to the position momentum uncertainty. Time energy uncertainty. In fact, we will see that the time and energy variables cannot be considered as conjugate variables analogous to the position x and the momentum p variables, which, when regarded as operators, obey the commutation relation given by operator x and operator p, that is the commutator of the operator x and operator p is equal to iota times h cross times operator I, which is the identity or the unit operator. And the reason why we cannot consider the time and the energy variables as analogous to the position and momentum variables is the fact that when we cannot talk of delta t, that is the spread in t, at a given single instant of time, nor is it possible to define iota times h cross times partial derivative with respect to time operating on an instantaneous wave function. Thus, even though we do have the commutation relation in the time and the energy variable given by iota times h cross times partial derivative with respect to time, and time is equal to iota times h cross times the identity operator I, it cannot be considered as analogous to the commutator of operator x and operator p being equal to iota times h cross times the identity operator I, and therefore one cannot derive the above relation using the analysis given here. So students, now let us summarize what all we have learned in this module. After studying this module, you should be able to know the definition of the root mean square deviation and its significance. Secondly, you should be able to deduce the generalized Heisenberg's uncertainty relationship for any pair of canonically conjugate variables corresponding to non-commuting operators. Then you should have learned how this general relation is used in the case of 1. Position and its conjugate momentum variable, and secondly between the components of the orbital angular momentum. You should know the state in the coordinate representation which corresponds to the minimum uncertainty product, that is delta x delta px is equal to h cross by 2 in the position and momentum variables of a particle. Then you should also know why the uncertainty relation in energy and time cannot be considered analogous to the canonically conjugate position and momentum variables. Thank you.